Let me start this one. Let me see whether live is going on correctly. Yes, it is. Okay, so this is a new link. I'm post, copy, paste here. I save. Okay, so we are working on this part 559, right? So it says we find E11. I think this should be the one. We do equation 559. Okay, so equation, we have to see E11, right? So we go back. E11 is this one. E11 is like EXX, but I think we can go back here. So, let's see. This one, right? Let me do this. $532. This is $532. So this is 532. It's 37. I'm sorry. It's 37. So then E11, we can see E11 is 1/2 partial 1 U1 plus partial 1 U1 plus partial 1 U gamma partial 1 U gamma, and this gamma summation. Gamma is summation, right? So then this is like this partial 1 U1 plus 1/2 partial 1 U1 U gamma partial 1 U gamma. And here we assume U gamma small quantity. Okay, U gamma small quantity. U gamma is small, so we can neglect this one. So we obtain E11 partial 1 U1. Okay, that's this. That's the thing. Let me see. 559. Assuming small displacement derivatives, we find small displacement derivatives. Interesting word. Small displacement derivatives. Anyway, I think it's an interesting word. Small displacement derivatives. So we have this. So we can do the same. E to 2, E to 2, still you can neglect this part, this term. So E to 2 is partial to U2. Counterclockwise rotation, theta 1, 2 of OA, theta 2, 1 of OB are obtained as. See, this one is actually, you can do this. You have OA. Look at this. OA is like this. See, vector OA is dx1, 0. Vector OB zero dx2. OA and OB. Right? So then we have primed point. See, so we consider rotation. Okay, so we consider OB, OA. I can say. So if you have some vector, let's see, V, and rotation, U. Here you have rotation, theta. What is this rotation? So U counterclockwise rotation is something like this. Cosine theta minus sine theta, sine theta, cos theta. This is the counterclockwise rotation. Yeah. So if V is 1, 0, this go to cos sine theta. If V is 0, 1, this goes to minus sine theta, cos theta. So this means this one, this is 1, 0, go to here. This is theta. So if you have 0, 1, this go to here. This is minus sine theta, minus sine theta, sorry, minus sine theta, cosine theta. Yeah. So this is 0, 1 is here. 0, 1. 0, 1 vector go to minus sine theta, cosine theta. 1, 0 vector go to cosine theta, sine theta. So the rotation matrix for counterclockwise is this, right? So we have this OA. We consider, we regard this change, this deformation as rotation. So OA is not exactly same, but we consider the rotation. See here, cos theta minus sine theta, sine theta, cos theta. Yeah. Then here, you have dx1, dx2. No, this is dx1 and 0. So then you can see now the rotation is small. Okay, theta is much smaller than 1. Then this rotation matrix can be approximated to 1001. No, sorry. This approximated to be 1 minus theta, theta 1. And then you have dx1, 0. So you have dx1, theta, dx1. So you call this 1, 2. You call this theta 1, 2. This theta, you call theta 1, 2. Right? So then if you see, let's go to this way. A is this. dx1 partial 1 u1 dx1. This one is actually after deformation dx1 plus partial 1 u1 dx1. Am I correct? Sorry, this is dx1 plus partial 1 u1 dx1. Partial 1 partial u dx1. Partial 1 partial 2 dx1. Okay, easy. Partial 2, partial 1 partial 2 dx1. Partial 1, okay. Okay, this way. Yeah, so you can see the both side. See both side. Then we actually, so this is the approximate equality. This is still approximate. So here, what is the small value? Yes, small value is this. Small value we neglect. Then you can see dx1 is dx1. Then theta 1, 2 is partial 1 partial u. So now we obtain the relation like this. Theta 1, 2 is partial 1 u1, u2. So that's this. First, oops, where is it? Theta 1, 2 is partial 1 u2. We can do the same thing to theta OB. See, I can do OB. OB, what is OB? OB is partial 2 partial u dx. This is partial 1 partial 2 dx. dx2. dx2 plus partial 2 u2. Partial 2 u1. Partial 2 u1. I'm sorry, this is partial 2 u1. Partial 2 u1 dx2. dx2 partial 2 dx2. Partial 2 dx2 partial 2. Okay, so this is OB prime after deformation. And when we consider the rotation part, we approximately equate this one to the rotation matrix, which is 1 minus theta, theta 1. It's a counterclockwise rotation. Then here we call this theta 21. Then original one, OB, is 0 dx2. Right? This is OB. This is OB, right? So we obtain this is equal minus theta 12 dx2 and dx2. So neglect small quantity. Yeah? Small quantity is this neglect. So then we see here dx2, dx2. Then partial 2u1 is minus 1 theta. So we obtain the final relation theta 1, 2 equal minus partial 2 u1 this way. Yeah, that's this one. Okay. So then the engineering shear strain gamma 1, 2 and the mathematical shear strain. It is interesting. Mathematical shear strain and engineering shear strain is a little bit different. Measures of the change in angle from the original 90-degree. Okay, so this is something like this. Originally, this is 90-degree. Then you have here, this is theta 1, 2. And this is theta 2, 1. So, and theta 2, 1 is actually a negative value, right? I think. Actually, negativity is here. Negativity is this one. Okay, so we can if we okay, so I can say this way. This is like clockwise. Clockwise direction. If we consider the clockwise direction, this is minus 1, 2, 1. Yeah. So this is negative. So this one is positive because this is clockwise direction. So this new shear angle, this one, this angle, green angle is 90-degree minus theta 1, 2 plus theta 2, 1. It's a little bit complicated. So, and this part, right? This part is gamma. Is this minus gamma 1, 2? And gamma 1, 2. Because this one, 1, 2. This is theta 1, 2. And this is minus theta 2, 1. Yeah. So what we consider above is minus 1, 2 plus 2, 1. It's a little bit 2, 1, 2, 1. Okay. So this is should be a positive, right? This is positive. Seems like this is positive. 2, 1 minus 1, 2. No. 1, 2 minus 2, 1. Okay. 1, 2 minus 2, 1. Okay, so this one is negative. Theta, I mean here is this. This angle changed by deformation from 90 degree to theta. And what is the theta value? Which is 90 degree minus gamma 1, 2. Then gamma 1, 2 turn out to be theta 1, 2 minus theta 2, 1. This is gamma value. Gamma 1, 2. Okay. Engineering a mathematical shear strain. So where is the mathematical shear strain? I think you had somewhere above. This is a mathematical shear strain. So you have E12 is half partial 1 U1 plus partial 2 U2 plus ignored. This is ignored as a small quantity. Yeah. So then, I'm sorry, partial 1, 2, 2, 1, partial 1, 2, partial 2, partial 1. I don't know, U1. Yeah, then this is like theta 1, 2. And this was minus theta 2, 1. Am I correct? Yeah. Partial 2 U1 minus. Yeah, I think so. So here we have same thing. We have E12, 1, 2, E12 equal 1/2 theta 1, 2 minus theta 2, 1. Yeah. And then the infinitesimal rotation R12 is defined as the average of two rotations. So this is 1, 2, infinitesimal rotation is average of two rotations, theta 1, 2 plus theta 2, 1. Yeah. So this is theta 1, 2, and this is theta 2, 1, average, infinite. And we actually had a pretty much long discussion with Professor Na, and we concluded this sentence here is just confusing. So don't worry about it. This one, don't worry about it. So we can ignore. So then we go to the next section. Deformation ellipsoids. This sounds difficult. Deformation ellipsoid. We consider a small sphere in the undeformed configuration. dx alpha equal k squared. This is summation convention. See, you should see this alpha is summation convention. So that means dx1 square plus dx2 square plus dx3 square equal k square. So this is the equation for sphere with the center at x. In the deformed configuration, the center has moved to small x. The map of the sphere can be found from dx alpha is partial I x alpha, partial j x alpha, dxi dxj, g ij dxi dxj equal k squared. As gij is positive definite, the preceding quadratic form represent ellipsoid. I'm sorry, I'm not familiar with this math, but this represent ellipsoid. If G is positive definite, Gij is positive definite, this equation represents ellipsoid, known as the mathematical ellipsoid of Cauchy. See figure 5.5. Similarly, a sphere d small xi equals small k squared in the deformed configuration is a map of an ellipsoid. dxi small x equal partial alpha small xi partial beta small xi. Excuse me. And d large x alpha d large x beta equal g large G alpha beta dx alpha dx beta equal k squared is the undeformed configuration. In the undeformed configuration, this is known as spatial spatial ellipsoid of Cauchy. Spatial and mathematical ellipsoid of Cauchy. Spatial and material ellipsoid of Cauchy. Actually, this is mathematical. Sorry. Yeah, so you have sphere in material coordinate, and which is mapped to ellipsoid in spatial coordinate. If you have sphere in spatial uh, uh, spatial coordinate, yeah, ellipsoid, sphere in spatial coordinate is a map of the ellipsoid in material coordinate. So this map to this sphere. Let me change color. So this sphere map to this ellipsoid. Okay. So then lambda. Let me see. Let us concentrate on the spatial ellipsoid for the time being. The directions of the three axes of the ellipsoid correspond to the direction along which the stretch lambda ds over d large S is stationary. What does it mean? Along which the stretch is stationary. What does it mean? If n is a unit vector pointing in the direction of dx inside ellipsoid in the undeformed configuration, we have n alpha equal dx alpha ds. By dividing equation 564 by ds square, we find something. To find the directions n along which lambda n square is stationary, we have to extremize it subject to condition that n is a unit vector. For such constrained extremization, as discussed in chapter 2, we use the method of Lagrange multipliers and define a new function, where G is the Lagrange multiplier setting something. We obtain system of simultaneous equation, where we have used the fact that G alpha beta is symmetric. In expanded form, we have something like this. Let me see. Polar decor. Okay, so let me stop for now. Let me stop up to here. We will consider this one next time. So next time we do This part I don't understand much. See, the three axes of ellipsoid correspond to the direction along which the stretch is stationary. Okay, okay. You have some sphere, and you have ellipsoid, right? So in this direction, this if mapped to this part. Yeah, so this is like a dx, and this is dx. So you can see, you can consider small change, like small change in this way. But then here you also have small change. So this is called stationary. See this part mapped to almost unmoved part. So this direction is stationary. Yeah. So the three axis of ellipsoid corresponds to the direction along which the stretch is stationary. Yeah. So okay, we finish. We stop here at this point. So next time we start from page 61. Okay. So we do 61 next time. So next time, let's see. So we do it from page 61.